I did not get anything. Sweet. I mean, you can also just accept, but like if you get the Zoom recording.
Yeah, for sure.
Okay, so you're screen sharing. I'm gonna mute. Let's mute our mic. Wait, is your volume down?
Are we doing my volume on?
Yeah.
Okay, I'll turn my volume on then. Okay. All right, hi everybody. So I think I am going to be talking a little bit today about cognition and comprehension in language models. I want to apologize a little bit in advance if I'm a little bit muddled. I just came back from a conference in Montreal today, which was super interesting. But yes, please bear with me if anything is a little bit muddled and stop me and ask for questions. And I'm happy to go into anything further, like, just depending on what everybody's like interest is, because it's going to be a little bit of a sprinkle of everything. Okay, cool. So, I am in the natural language processing group here at University of Minnesota. And part of what's really interesting about working in natural language processing right now is that obviously like language models are really like popping off with like a lot of different tasks, right? And one of like the very vexing things about this is that the technology is in a place where like the number of theoretical results that we actually have to tell us about like things like what language models can do and can't do and whatnot, theoretical results are very limited. And so a terminology that's been kind of taking off in the language model research space recently is jagged edge. Or jagged edge frontier of language models. And it's used to kind of describe this type of problem or situation, maybe I should say, that we see here. Sorry, I'm trying to like get my pointer going and I keep on accidentally turning on my annotations. Okay. So what we would probably expect to see, right, if we have this graph of like, basically like performance and task difficulty on the x-axis, we would probably expect to see something where like, we're starting up like high and then we're, dropping off at some point, maybe it's a cliff, maybe it's a curve, like, but that's kind of what we would intuitively expect to see. But instead what we have for language models is this like very, very unpredictable jagged edge looking graph where there seems to be little to no relationship sometimes, depending on the task that you're looking at, between like how well the language model is going to do and how difficult the task like seems, right? So for example, there's this math data set that is one of the standard benchmarks that like all of the big language models are tested on. And this is like an example of some of the items from there. It's like college math problems, right? And a lot of the state-of-the-art language models are scoring like, I don't know, like 70% accuracy on these, things like that. Some of them higher, obviously. You can, industry is fine-tuning them to get medals in the Math Olympiad, right? So they can do some very impressive things that definitely indicate something that's going on like a little bit deeper than like, like literal parroting, right? So there's some very sophisticated pattern matching at least happening to allow like these really sophisticated tasks to be completed successfully. On the other hand, there are certain things like questions like how many times does O appear in the word bookworm? I don't know how familiar people are with examples like this, but this sort of thing is like is very, very, very common failure point. And so yeah, this is the landscape that we're dealing with here in natural language processing. And so we want to think about things like what kind of things are we talking about when we talk about language models being able to like do these tasks? What are we talking about when we talk about language models being able to reason, which is another really hot topic for especially industry these days? And yeah, what does it mean to say that a language model is thinking about something, reasoning about something, or comprehending something, right? And this is obviously a really thorny question. It's like I remember, years ago when I was first like learning about you know, computational approaches to language and things like that. The Searle's Chinese room argument was something that we talked about a lot in those classes, and it's very strange to think that we're living in a world right now where there's like an actual, like, it's no longer a thought experiment, it's kind of like real life. And it's still a very difficult problem, right? But now we actually kind of are very pressed to solve it. So the nice thing about this collaboration that we have with the NLP group and Textgroup is that, psychology, linguistics, all of these areas have kind of made so much progress over the last several decades in terms of understanding these like really complex and smart systems, like aka humans, and how they do this information processing. And so the general motivating strand behind the projects that I'm going to talk about today is kind of trying to use this as a jumping off point for how we can maybe understand a little bit more about what kind of information processing is happening in language models, right? So as I'm saying information processing view here, I don't really want to get into like the philosophy of like mind and consciousness and like deliberate thought and things like that. I'm just going to stay grounded in this like information processing view of cognition for both humans and machines today. But if anybody wants to talk about any of the other topics or has like thoughts about them, I'm super stoked to hear that sort of thing always. All right. Main goals. We want to dissociate this idea of like genuine understanding and comprehension from something like sophisticated pattern matching, right? And this is super hard to do when you consider that language models are trained on like, I forget what the exact number is, like several orders of magnitude times more text than anybody will see in their entire lifetime, right? So this is like a skill that's really, really difficult to comprehend with respect to the pattern matching aspects. And again, our tools are going to be some materials from psychology, linguistics, and also some more natural language processing oriented tools like prompt variation and representations from some of like the intermediate computations that the language model is going to compute before actually, generating a word, as language models fundamentally do. Okay. So again, I'm just going to be presenting some recent work because this is what I have on hand. And I know my Textgroup collaborators know this very well. And so first I want to talk about just some more low level stuff just with respect to like how we can think about maybe in context memory and language models, because I hope that's going to be some helpful like context and background information for when we switch to part two, where we talk more about like reading comprehension and kind of more like real world scenario, I guess. Okay. So basic background for experimental pipeline, just most important thing to know, this is like just literally copy and paste a diagram for a paper, so don't worry about like all of the parts. But the main thing to know is just that like all of these prompts get varied quite a bit throughout the every time we like give a stimulus to a language model, right? So we're going to be changing just like even like we have a few paraphrases, but the main thing honestly that happens is things like white space or punctuation changes. And the reason why we have to do this is because language models are still, like a lot of them are still incredibly sensitive to things like simple white space changes. So like this graph here is just showing the accuracy on the y-axis. This is a box plot of the accuracy for a specific task. The task isn't really important. This is a very common pattern. And this is the accuracy spread across all of the different types of prompts. So if we take like these 30 different prompts and like the average response, like accuracy for each of those, that's how much the performance can be affected just by things like just slight word choice changes or like punctuation, white space. So I say this both just as an FYI in case anybody is interested in doing some playing around with language models themselves. Definitely keep this in mind as something that's important to consider. And secondly, to say that this is sort of how we are estimating things like means when we're reporting results across data sets for the rest of these experiments. All right, so something that I have been really interested in recently is memory for language models. And so I'm thinking right now about like kind of two types of memory and language models. And the one that I'm going to be talking about today is this kind of like context-based memory. So this is just a little terminology in case, again, I'm very out of touch in terms of like what the like non-NLP centered conversations are around these terms. So I'm really sorry if this is like really boring information. But okay, so context window is how we talk about like the input text to a language model. So like every time a language model is generating a word, it's doing so conditioned on the previous input. And the previous input is going to be like, if you think of the common like paradigm for language models right now, where they're like in these chatbot forms with dialogues, everything in the current conversation is part of the context window. And any of this text that's like inside the current conversation, we call like in context. And so I'm going to be talking a lot about the memory for text like inside this context window, as opposed to long-term memory from like pre-training, right? So of course, I think we all know that language models, over the course of being trained to predict the next word, are able to also infer a lot of like world knowledge, things like Paris is the capital of France, right? So we can think of that sort of thing as like basically equivalent to the long-term memory in language models. And yeah, this is fixed. Again, I think everybody interacts with language models and understands this, that if you have a conversation with a language model and then you switch to a different context, the long-term memory is like not updated, right? And it also, the other cool thing though is it also doesn't like it's not really subject to any of the transformations that might happen in people, where like repeated access leading to mutations, things like that. It's pretty stable, but it is fixed. So in contrast, we're going to be talking about things from the context window. And this is really interesting. If I just focus on this first bullet point for a minute, the architecture in the current language models is the transformers-based architecture, which not that important really for this conversation. I just bring it up because this is actually a theoretical result with respect to the transformer architecture, which is very exciting. That's why I have an exclamation mark, because if you remember, I said earlier, we do not have a lot of theoretical results. So this is super cool. So the amount of text the language model can repeat from the context window is scales exponentially with the with a parameter in terms of that describes the size of the transformers, basically number of attention heads for anybody who's a nerd about transformers models. So this is really, really interesting. So I haven't actually tried to find like empirical limits on this for the language models that we're working with, just because it takes forever to compute like you know, to compute all of these tokens a billion times in a row, and like it's really boring just watching the model like repeat everything all the time. But yes, theoretically this is like a very, very, very easy thing for a language model to do. So what we want to know here is what it might interfere with the language model's ability to have this like perfect access to all of the text in its context window, right? Because this is the thing about the language models, right? Is that like when a language model has this conversation in this like context window, and then they're generating the next token in this context window, there is theoretically perfect access to like everything else that's already happened, right? So this is very, very different, of course, from how humans are interacting with language, right? Where even if we're like even obviously during speech, there's like all sorts of difficulties with having perfect access. But even if you're reading and you can like look back on things and everything like that. Anyway, very interesting, very different. Let's talk about it. So one of the things that is maybe picking up a little bit of speed right now, in language modeling is this idea of like, can we talk about maybe like working memory in language models? And this is partially related to just like the broader interest in like intelligence for language models. And I think people are kind of interested in working memory because it's often comes up in context of like, individual differences in working memory being tied to like other individual differences across, various tasks. So it maybe has some appeal, I think, from the computer science side as like a potential for like maybe like a benchmarking type thing if it can be maybe developed a little bit further. So there's been some prior work that does the end back task on GPT-3. So we've recently replicated that result for some other models. So I'll share that in a moment. And we're also going to look at some like digit spans and complex spans and just see like kind of again like a language model should be able to theoretically do these perfectly because there's no problem with the the encoding is theoretically perfect. So we're interested to see kind of like what happens across these different tasks. All right. So first thing that is pretty interesting to me is that the forward digit span for a language model is orders of magnitude higher than the backwards digit span. And as I said, I have been a little bit lazy about this because I haven't actually found an upper limit for the language models. I have done some like light experiments for 100 tokens, got bored. It all looked really good. The last like set of rigorous experiments I did was for 50 digits and it was like all perfect. So like this is just I do apologize. I do need to finish these experiments. They're just incredibly boring because like the language models are really, really good at it. Backwards digit span gets more interesting. So this is a look with the x-axis is just a bunch of different language models. And these different bars are going to represent different lengths of the sequences that we're looking at. So kind of organized from like 7, 15, 20, 30. And as we can see, for the 7, we have like some models who can do 7 like really, really reliably, can reverse correctly. And once we get up to like 20 or 30, that's where performance really starts to drop off. And this is, I just think this is so interesting because it's such a dramatic difference from the forward digit span. Yeah.
So, quick question, because
Mhm.
maybe I'm like thinking about backward digit spans
Yeah.
wrong. So forward digit span, you just
Oh, yes,
giving
thank
it-
you. Yeah. Just so repeat the numbers in sequence. Yeah.
and then how would the backwards version of that look?
Yes, thank you so much for asking this question. This is fantastic. So the backward digit span is we're going to use the exact same sequences that we did for the forward digit span, and this time we're just going to change the instructions to say repeat it in reverse order. Yeah. So
Interesting.
yeah, so just this reversal operation throws like a really big wrench into the recall process. And I really want to talk a little bit more with some of my friends in like the more like mechanistic interpretability side of things because oh, Andy, yes.
This is just a question about the graph there, which is it looks like some models were tested with all 4 different lengths, whereas others weren't, and so like the Queen 270, I just see the blue bar, and the red, green, and purple bars are for that. Do you understand what I'm saying?
Yes, yes.
So
This is another another
I'm
excellent.
looking for 4 bars for each language model, and I'm not seeing it. So can you just help me out with that?
Yes. So these are exactly the language models that I want to point out because the way we can actually read like these little strings at the bottom here, and I apologize because as I said, I'm just like literally copying some information from some recent papers, so they're not designed very well for this particular meeting. So the way that we can read these is the very last part of these labels, like the number followed by the B. That's the number of parameters in the language model. So the language model size. So the smaller language models here are like 9 billion, 7 billion, and 8 billion parameters. And these are the ones where, as Andy pointed out, we don't see like a bar for all of the numbers, which is because it's 0. So just not able to complete any of them. And these are, I'm not sure the best like metrics in terms of this is just a strict accuracy, like so you don't get partial credit for like doing some of the sequence. I have computed like some Levenstein distances to try to like maybe get a more partial or more nuanced understanding, but it's a little bit more difficult to interpret. So I'm just sticking with like the strict all or nothing approach for this. So yeah. Right. So these models, some of these small ones, and in particular, like yeah, it can really only do like the length 7 and really, really fall off very, very hard for these larger lengths. So yes, this is super interesting in my opinion. Um, Why is reversal so hard? I imagine that there are some transformer architecture related explanations for this. And I'm not sure how much of it might be a result of training versus like an inherent consequence of the design. This is something that's always really hard for us to tease out as well. It could be that during training, the ability to associate like in a forward sequence like from a starting point and just like continue your lookups in that way might just be something that you get for free from training, and it might just not be so trivial to start in one position and then compute like backwards. The way these models work is they're very like forward looking, and I actually realized as I say this that I really shouldn't because I don't really have the visuals or the time to get into this comment. But yes, the takeaway here can just be that like this is interesting. I wish I could say more about why this is. Likely has something to do with this like lookup mechanism in terms of like, just looking within this context window and searching for text. So there's something that makes this very difficult for something that's not just a simple like forward repeat perfectly. Okay. So moving on from digit spans to complex spans. So brief breakdown of like what these complex spans are going to be looking like. Basically just pairing some kind of task with um some kind of like operational task or like I don't know. I don't have the vocabulary. Somebody I'm sure here could help me out. With like the actual memory task, right? So we're going to be interleaving something like making a judgment for like whether or not a sentence makes sense, with remembering a word, and then at a certain point, after like what is it, 2 to 7 trials, something like that, 2 to 7 words being presented, I should say. Um, the question is like, recall all of the words since like, the last time we did this word recall thing. The other complex span that we look at is the operation span, which is just evaluating the validity of an equation interspersed with some numbers. So, number version, word version, cool. So one interesting thing for me when I was thinking about doing these complex spans for language models is because of this like perfect access to memory and just like the way these language models work, there's not the same concept that you have for the analogous like human study, right? Where like you have to do some tasks, you get this word that you're keeping in mind. Okay, so you're like trying to remember it, and then you get another task to do, and you have to do that task while keeping the previous word in mind, right? So this is like not at all what is happening in this kind of dialogue in a language model, right? Because it's very, very sequential. Like when we have the next, after saying like remember code, if we give like another sentence here, the language model doesn't have to do anything to keep code in mind. It's there for free, right? So I was thinking, like, is it better to, set up the task like this with like, just full fidelity with the human version, despite, the lack of spiritual fidelity, for lack of a better word. Um, so I also tried this like all at once setup, which is basically like having the model hold and like not respond to anything until the recall point. And then the model at the recall point, it's like, okay, so now do all of the operations and recall all of the words, just to try to like simulate that idea of like, having to do both at once, kind of. Again, the model does generate a token one at a time. So it's not quite the same. But I wanted to try this out. It wasn't very interesting because the results are really similar both ways, it turns out. And the other interesting thing about this is that the breakdown across the different span lengths, so like whether we're trying to recall like 2 to 7 items, there's not really much of a trend in terms of like accuracy versus item, which is again really different from like this backward digit span task, right? Where there's this really clear trend from like, the length and the accuracy. I have some ideas about why this is, and this is something that I did really recently, so I haven't actually been able to dig into exactly why this is more. But I think there's definitely an evaluation problem here, which is that the language models Oftentimes in this task will recall like too many words. So like they might recall like just everything like from the beginning or like even the entire conversation, just repeat the whole conversation, right? And so we can think of that maybe as like a little bit of a crutch because like as we talked about with the digit spans, right? It seems like it's very, very easy for language models to just repeat in the context window. And maybe like selecting the relevant parts only to repeat is a little bit more difficult from just repeating verbatim. So especially in this like all at once task, I would observe like, the language model just like literally like going through like in order and like interleaving some answers, but still just like it really did not want to do something like all the sentences, sentence one, sentence two, sentence three, all the words like word one, word two, word three. It's very much just like kind of replaying the conversation. So that might be a little bit of a confounding factor where, some of the evaluation just gets very tricky because again, it's like, this is an interesting task, to do for language models, but it really is taxing like very different, abilities than it is for like the human participant version, right? So, my sense is just that the evaluation needs to be like, updated a little bit more. But yeah. I'm also like not doing any kind of penalty for hallucinated words in this either. That's another thing that happens. So yeah, if anybody, has ideas for evaluation metrics for this, definitely let me know because I'll try anything. All right. Yes. So selecting problem, I want to talk about a little bit briefly, just with respect to this idea of like, having all of these tokens in your context window, and then the goal, right, is to generate like the next token, right? So this is our next token that we want to generate. And what we do every time we generate is we compute some like attention map with like everything that's already happened and how strong the relation is between every other token and like this next thing that we want to generate, right? So this is a really non-trivial task in a lot of these kind of I don't know what to call it, this sort of these like laboratory artificial experiment kind of tasks, right? Like it's very unusual because it's always very like, you do like every other thing or like it's not I don't know. I think this is just a very hard problem to like just based on these instructions come up with an intelligent strategy for this selection of like what the relevant tokens are, right? And this is like obviously also not something that is going to come up a lot in the naturalistic training data either, right? So yeah, it's interesting.
I have a question.
Yeah.
Like what you said, this is like not like not a natural experiment. Would you referring to like more like a simulated experience for language models or more?
Oh, no, I just mean like in terms of like this is not like a naturally occurring task.
Yeah.
Like, yeah, so you don't really.
It's like a hyper.
Yeah, exactly. And you don't really have any like examples or like there's not like a lot of not like a lot of examples of these kind of scenarios where it's like, oh, every other trial we do X or like, ignore every third word or something like that, right? So obviously if you have like a really strong like I don't know, like I would argue that if you truly have a good grasp of meaning in language, this should be possible, right? Because it's very simple, these tasks, right? Like it's very clear, it's very unambiguous, like kind of how to solve them. But I think there's something in terms of this mapping between the semantics of the instructions about like, locations in the text stream and things like that, like mapping those to the actual computations of these like of these lookups basically for things that I think that mapping is like might not be something that you can learn very well from like just reading text. Yeah, as opposed to learning something like Paris is the capital of France, you can really see how you would learn that association. Yeah. Yeah, very speculative. I don't have any empirical evidence for this, but yes. So yeah, speaking of this selection problem, when we run the n-back test, this is kind of like the most human-like we get with respect to like accuracy and I don't have a good graphic for this, so I'm gonna like annotate on Zoom just to review. So n-back task is we have like this stream of stimuli, right? So maybe we can imagine that they're letters. Oh my gosh, drawing is so hard. This reminds me of trying to teach on these things and doing a terrible job. Okay, so we have a stream of letters, right? And every time we get a new letter, our task is going to be to say if it's the same letter that we saw n trials ago. So if I'm doing this like letter stream here, okay, so let's just say I just got the letter B and we're doing the 2-vac test. So I'll look 2 letters ago was Y, so I'll say no. Then I get a new letter and it's X. I look back 2 letters ago, that was X, so I want to say yes. Okay, so this is the n-vac task. 1-vac, 2-vac, 3-vac. And yeah, interestingly, the difference between language models and humans here is like a little bit closer. So again, this is like it feels so for the literature that I found on the NVAC task for like with respect to things like, you know, working memory or executive functioning in human is framing it very much as like an updating problem, right? Because you have like the state and you need to continually update it to reflect like the most recent letters that you've seen. And again, for language models, since they have this very interesting situation where they have this perfect access to everything that's already happened in context, I feel it might be more useful for language models to frame this again as a selection problem. So we need to be able to select exactly the letter that we saw like n letters ago. And apparently this is very difficult, despite, again, the fact that language models can, you know, have like a forward digit span of a billion, like so good that it bores me. And this is like you know, not so simple. Yeah.
I have a quick
Yeah,
question.
for sure.
What are the instructions like for something like this for an LLM?
Yeah, so the usual approach is to basically use the same instructions that would be for like the
human.
human participant. Yeah, yeah.
I'm like, part of me is like, is the LLM like trying to mimic human behavior, or is it like trying to quote unquote not cheat?
Yeah, I mean, like it's of course like really hard to ascribe like
Like
intent.
Yeah.
Yeah. There's certainly not. So these like instruction tuned language models have some training to follow instructions. So we can say that there is some incentivization to follow the instruction. And we do see like in the other tasks, like sort of the superhuman performance. So from that, I would guess no, but that would be, that would actually be like super interesting. I know there's some folks who have really strong backgrounds in I don't know, things like neuropsych, like there's some teams at NYU right now who are trying to build like a human-like language model. So yeah, in their case that would be yes. But yeah, for this one, I suspect not, yeah.
Would that be like, for example, when they're doing this kind of like, I would say like experimental,
Mm.
like very traditional experimental
Yeah.
psychology text, like would they like, I don't know, would they do one after another? Or like, for example, do they do like end back tests for one day and then like the backward thingy for another day?
Sorry, I lost the premise.
Like, are they doing multiple
Multiple
tests?
tests.
Oh, in the
Like,
same
yeah.
context. Oh, that's really interesting. No, these are all new contexts for each of, yeah. Yeah. Another kind of factor that's probably relevant here is that this task like and back, you know, takes place over like multiple turns in a dialogue. Whereas something, and so does complex span. But something like the digit span is like we just do 1 turn dialogue. So it's just like input, output, that's it. And the reason that this is interesting is because over like longer contexts, these like attention maps are like more difficult as well. So it's like a little bit of a confounding factor that it's hard to control for, yeah. But yeah, that would be really interesting to do like to alternate between the tasks. Yeah, I imagine it would only hurt results in terms of like performance level, not in terms of like interest, but yeah. Okay, cool. So, yeah, summary kind of like the tasks that we've looked at. These are accuracies. And yeah, as I said, OSPAN or operation span, reading span, these complex span tasks. I do not think I have the best evaluation for these. That's why I have the question mark there. So yes, there's nothing new or interesting to look at here. I just wanted to add this for a sense of completion for all of us as we wrap up this section. All right. So again, not to, beat a dead horse here, but this in-context memory for LLMs, what's really easy is just verbatim recall. What's harder is going to be things like updating, or maybe it might be better to call this selecting, sequencing or operation. So I am really interested in kind of trying to tease these apart with like, just some follow-up like novel tasks, like not from any experimental psychology. But again, just given kind of like what we've observed here, where it's like, okay, is this like an issue for the backward digit span, for example? Is it an issue because there's an operation? Like, should we be thinking about this as like you have this forward string and now you're applying an operation of reversal? Or should we think of this as like a sequencing problem where like we're trying to like compute these lookups in a specific sequence? So yeah, that's kind of the idea for future work, is trying to figure out like a little bit more about exactly how we might think about these different aspects, I guess, of LLM in context or working memory. Yeah. Okay, cool. So, one thing also that we want to do just like really briefly, is look at like just some other like executive functioning related tasks. So like basically ideas if LLMs have like this really good like working memory performance, like do they also have really good like just any other kind of experimental psychology test performance, right? So wanted to do something for like inhibition and attention. Really kind of tricky because so many of these are like, like really brief stimulus presentation or like really like reaction time focus. So it's like really, really difficult to adapt because that temporal element just like isn't there for language models, right? So one thing we did try though is like this flanker task. And the way this setup works is something like this. So you'll have like two different responses that are going to be mapped with two different stimuli. So for example, you can imagine maybe like a right button being associated with like the letter X or C. So if you see X or C, you need to hit the right button. Left button for letters B or V. Okay, so again, very very experimental psychology, very like not naturalistic, right? Okay, cool. So we're gonna ignore everything but the center letter when we're doing this task. So basically, we can have two different kinds of stimuli that we'll see here. We could have something like this, where the center letter is C, and then these flanking letters are X, so they both map to this like right button response, right? Or we could have something like this, where the flanking letters map to one response and the center letter maps to a different response. So these are going to be the congruent and the incongruent trials. Of course, the idea for this task in the experimental psychology is just like measuring the reaction time and talking about, the delays due to having to inhibit the flanking response. So yeah, when we look and try to do this for language models, we find really consistently, even for like the larger models, that their accuracy for the incongruent strings is like really low. And one possible explanation for this is actually just like a tokenization problem. So we know that language models, for their input text, they make tokens that usually, but not completely, map to like a word level, right? So the concern here is that especially if we do something like, let's say we have a string like this, if we have like B, B, C, B, B, there's a danger that the language model is going to tokenize this with BC together because, this is a common, like is in the year BC. Okay, so we have this danger of the tokens not necessarily corresponding to the letter, which you could argue is an unfair, mean thing to do when you're setting this up. And this, as an aside, this tokenization issue is also, why things like the how many O's in bookworms question is so hard to answer for context. Because they're not looking, they don't have really good access to the letter level representation. So yes, so I had set up this experiment, and then it was actually funny. I went to a conference, and one of the keynote speakers was talking about tokenization and how, how it's, there's some research right now where they're working and looking into, can we get rid of tokenization to avoid all of these annoying problems that, come up because of it. And I was at that talk and I was like, oh shoot, I need to redo this experiment and make sure there's no tokenization confound. So I did, and there wasn't, so that was nice. So yes, maybe we can frame this as another selection issue in terms of being able to map this idea of center letter into like looking up this letter specifically.
I'm sorry.
You know, it's
Could I also ask like
Yeah.
why the parameters are like different for different language model? I just noticed like for Gamma, it's like big like Queen is like obviously bigger than Gamma. And like
Yeah, you're looking at the
yeah,
sizes.
yeah.
Yeah. So the language models are built with particular fixed parameter size. So we have to pick a parameter size when we're running these experiments.
Yeah.
And the common setup is to do something kind of like we did here, where you pick some model families, just in case like there's something about maybe there's like some slight tweaks in the architecture. So I'm trying to think of like the best way to notate this. So we have some families. Gemma, Quen, and Llama. And then we have the sizes. So each family is just going to have like their own specific set sizes, and you get what you get. So the usual thing is to do maybe like a small, medium, large, small, large, something like that, just so that you have a variation across both families and parameters. So yeah, Gemma's small version just happens to come in size 9. Quen's small version just happens to come in size 7. Llama used to come in size 7 as well, but in 3.1 they changed to 8. And yeah, so that's a good question. Yeah, that's exactly why.
So it's not something that researchers pick, but
Yeah, exactly. So Google built Gemma, Meta built Llama, and Quen is built by a Chinese company whose name I forget. Yes. Which is kind of fun because with Quen, especially like the reasoning models that do, or like if you ever do something for Quen that's like going to take it too far out of like, the common space of like, texts that it's like seen during training or something like that, it has a tendency to start generating in Chinese, which is pretty fun.
I had a question about getting rid of the tokenization.
Oh yeah.
I mean, there must have been a reason to do it to begin with. I mean, can you just wipe something?
Yeah, great
Repercussions
question.
somewhere else.
Well,
you
so
know?
the reason to do it is more of an efficiency reason rather than like a helpful reason. So like not because it's easier to learn that way, but because it's more efficient to learn that way. Because if you do like a lower level of representation, the number of like combinations and computations that you have increases like quite a bit. So the strategy that they're looking at now are just like ways to like circumvent that issue and then be able to still have like this flexibility of like letter level representation, especially for languages like Chinese or Japanese or anything that doesn't have spaces in the language. The tokenization is really kind of a cursed approach. Yeah, if you even look at like the automatic tokenization, because the tokenization is all automatically learned, the tokenization does not make much sense, especially relative to like if you're used to like looking at the English tokenization where it's sort of like, oh yeah, words and morphemes and stems, you can kind of like be like, oh yeah, that makes sense. Yeah, it gets kind of crazy.
So does your computational cost then go up though? I mean, is this sort of a trade-off that we can do now because computation gets faster and faster?
Yeah, that's a great
So
question.
worry about the environment.
Yeah. Oh, we should definitely be worrying about the environment. Yeah.
But to simply say, I mean,
Yeah.
there's still trade-offs. That's not
Yeah.
computation.
Yeah.
Okay.
So I don't know a ton about it because the pre-training and things like that are really happening in like industrial contexts rather than academic ones. Sorry, I'm just looking around for. Okay, cool. Yeah, I'll just hop over here. And then maybe I know oh yeah, thanks. I know Andreas is gonna need some access to the screen if I go over here. Sure. Yeah. All right, sorry about that. Okay, so yes, tokenization, super interesting. Definitely recommend if anybody wants to like read more about this, I'll definitely find the research group that's working on this. I forget. His name is Luke. I forget what company I think maybe AI2 in Washington. I don't know. I can absolutely send some resources on this for anybody who's interested in this like tokenization question. Yeah.
Yeah, I guess it just occurs to me. I mean, can you think about it a little bit like the different kinds of writing systems and alphabets? Is that connected to it?
Yeah. No, these are great questions. But yeah, you definitely do see these effects of like not having this like letter level representation for stuff like this. Yeah.
Okay.
Yeah.
Thank you.
Yeah. So another interesting finding here from the flanker task, I think, is just that if you look at the like probability estimates, so the model is always computing like, just the probability of like the next token, right? So if we look at just the probability estimate associated with like the correct answer in the event that the model is actually going to produce the correct answer, which as we saw doesn't always happen. So if we just look at the correct responses, in the incongruent cases, there's like a lot lower confidence as well. So even if we look a little bit past accuracy, we can still see some effect of this like congruency manipulation, which is kind of cool. We talked about this a little bit with incongruent strings being hard already, with this idea of mapping the concept of counting or center onto like this context space, and with this self-attention mechanism. Okay. Other quick sidetrack that I want to get into is these like reasoning models, which I really, really, really dislike this name. So forgive me because I might go on like the same rant a few times here. So we have these reasoning models, right? And the way that these models work is that they will generate some sort of thought string before producing an answer. And the reason that this kind of came up as an approach is because it was already a pretty well-known and robust finding that if you, instead of just asking a language model a question, if you ask it to think step by step and like produce all of the intermediate computations that you would need to arrive at an answer, that the accuracy goes way up. So I think kind of the main intuition behind like why these reasoning models even like came into play was more like, hey, what if, I didn't have to tell the model like step 1 should be this, step 2 should be this, like whatever, whatever, whatever. I would rather the model figure that out itself, and then produce these, again, intermediate representations that can assist it in like, finding the correct answer and being able to produce it. And again, this makes sense in this, just based on the background that we've been talking about with like in context memory, right? So if the model can bring itself incrementally closer to the answer, when it comes time to actually answer, it's a lot easier to just like kind of like look up what happened in the end of your thought string than it is to like, look up the question, and, doesn't really have this mechanism to do a bunch of information manipulation in all likelihood. And again, I say in all likelihood because theoretical results are very, very, very hard to come by. Thought strings are trained with some heuristics. They're really based in like STEM problems typically, because that's like a big bragging point for industry right now, is being able to perform really well on some kind of like chemistry or math benchmark or something like that. So you'll see a lot of things like let me double check, or like trying to like rephrase or think about like if there's an alternate interpretation of the problem, something like this. And the model sort of is going to always be like a set, like you always have like this probability estimate over like what token comes next. And like the more diffuse and spread out that is, you can kind of think of it as the less confidence that has been computed for like what the answer should be. So sometimes if this confidence is really low, the model is incentivized to generate like a weight token to try to explore like some other path or something like that, right? And then once this confidence gets like kind of high enough, you will enter a state where you're most likely to generate the end thought token, which will then put you into a state where you're most likely to generate the answer. So not sure how clear this is, let me know. But yeah, this is the basic setup for how reasoning models work. So the annoying thing, sorry, it's very editorializing. The annoying thing about doing NLP research right now, especially if you're doing like kind of like benchmarking tasks like we're looking at here, is like people are always going to ask you like, what would a reasoning model do on this? And what would a reasoning model do on this indeed? Okay, so for the flanker task, we do find that the reasoning model is able to really, really improve the accuracy on these incongruent trials. And speaking of the environment, as Andreas mentioned earlier, this is like incredibly inefficient the way this works. We don't really see, there's no, I don't know why I said usually here. The average between the thought strings generated for the congruent and incongruent trial is the same, right? So even in the case where we have like all the same letters, this is just a substring of the total thought string, right? Like I'm being like, it's really annoying to read these thought strings because it's like basically they're really, really, really long. So I'm trying to select some of the more interesting portions, but I realize it's still very long-winded, so I apologize. So, looking at the letters X, 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 I need to identify the center letter. So there are 5 letters. The third one is in the middle. Let's count. 1x, 2x, 3x, 4x, 5x. So the center letter is X. Okay, good job. I did find one case. This is not very, I haven't been able to like read all of the strings yet. I may try to do some sort of automatic analysis of this at some point in the future. I did find one case of like being smart, which is, looking at the center letters, each of them is X, so the center letter is X. That feels a little bit more satisfying, right? But this is this case is much more common. We also see a lot of examples of just like diversion or like, oh, I don't have really the right word for this, but the model will stop working towards the solution quite a bit. So as I said, there's this tendency to generate these weight strings, but in this case, like it's like, wait, let me double check something. Like it's not a complex task, right? So we'll sometimes just repeat the instructions like 20 times to make sure we're not missing something. And it's like, it is really not that deep. Perhaps the example is a typo. I don't even know what that means. Like, okay. And something else is interesting here, which is sometimes the model will actually fail the task in its reasoning string. So we give 2 examples in the prompt. And so here it's referring to an example in the prompt that says like, if you receive the letters B, B, C, B, B, then you should respond with like the C response, right? And so here the model says in the examples where the letters are B, B, C, B, B, the middle letter is B. Which is not correct. Yes. And so I think eventually this model like gets to the right place. I think it decides that that's a mistake in the instructions or something like that, which, is a little bit offensive for me maybe, but yeah, so this is just some stuff that's like happening with these reasoning models. So, they're
So are they just too literal, or what's breaking down?
well, I
Actually,
think
it's so
they're
embarrassing.
I think they're trained in like math and chemistry kind of problems, and I think that the reasoning just doesn't really generalize very well. Yeah,
okay.
is my sense. But I haven't looked very much at like the math.
It seems surprising, because sometimes when something goes wrong, it's very telling.
Yeah,
Very
yeah.
realistic for digging into what to improve, what's going wrong, tells you what to fix. Yeah.
Yeah. So it's there's a lot of work right now in terms of like efficiency in general, like not in terms of for the thought strings, not in terms of like these particular problems, but just like even for the ones that the models are designed in, like you can really see like just like even successful cases like this, maybe you want to like shorten it, and there's like computational cost, like environmental cost, monetary cost, reasons for wanting to do this, right? So this is definitely an active area of research. So some other things, these are just funny. I should make sure that there are no other letters. I don't know what that means. Let's see. Oh yeah. Yeah. So this is another example of like not under like improperly interpreting like the incongruent string in the example. Wait, maybe the letters are arranged differently. Again, this is very like nonsensical. So yes, I do not like reasoning models, as you can probably tell. Reasoning models can improve the backward digit span. This is not something that I've looked into because the thought strings as much, because it's very hard for me to process what's happening with these very long strings in the reversal operations. So it's like a lot easier to like look at these and kind of see like interesting things that are happening than it is to look at like a bunch of lists of numbers. And like the main tendency for these models will be to like list out like make a numbered list of like 1 digit 1 2 whatever the second digit was, like all the way to like 30 or whatever, and then say like, okay, I need to reverse this list. And then like sometimes it will make an explicit map, and then it will like literally verbalize this whole thing, like 30 maps to the first position, 29 is going to be the second position, and like literally verbalize that the entire time. So that's one strategy. I don't have a lot of insights onto this though. I might skip this last, or yeah, I think we're about done on time. So I did not really get into kind of like some of the cooler stuff that we're doing, but I just wanted to throw this out. This is one of the, I think this like the memory aspect is important for kind of understanding like these other studies that we're doing for more like comprehension focused things. So one of the interesting things that we're looking at recently, with our, yeah, ongoing collaboration with like Textgroup for this is like these coherent and incoherent stories. And essentially we find that the language models, like if we look at the location of incoherence, this is like a heat map where the yellow is indicating like ability to separate the incoherent and the coherent stories. And then by the end of the story, this is very, very muted in most of the models. So, and then we're also looking at kind of how the models like actually respond to explicit questions about the coherence of the story, and their ratings for the incoherent and the coherent stories are really similar with respect to both story coherence and story quality. So there's indications of some interesting things going on here. This might just be detecting some like unexpectedness or something like that. And there are also obviously a lot of implications with respect to what we were talking about before with this like in context memory and like making associations between different parts of the text and whatnot. So super fun stuff for a lot of this. Yeah, as I said, I don't have, did not just threw together some recent results. So sorry for the pacing not being great. But thanks for the wonderful questions and discussions. Yeah.
Awesome.
Yeah.
Welcome.
Cool. And yeah, anybody on Zoom, if you can always feel free to unmute or write in chat or anything. Can answer whatever.
Yeah, if people have time, we can spend like maybe 5 minutes.
Like 4 right now?
Yeah.
Yeah.
No.
Yeah, I mean, if
I'm
anybody
gonna
has
hang
to
out for like
go.
5 minutes.
Yeah, I can hang out for
We
5
can do
minutes,
that.
yeah.
Wait.
Yeah. If somebody starts looking impatient outside.
Yeah. It's pumping up.
Any questions on Zoom?
Just quickly sorry, Yujong, please go ahead.
Yeah, it might be a stupid question, but could you share a bit more how did you collect and analyze the test result from the LLM? Yeah.
Yeah, in for like across all of the experiments, or is there a particular experiment that you have in mind?
Um, uh, Anything you can, yeah, briefly share. Not that much technical, yeah.
Yeah, sure. So basically, for all of these experiments that we've run, we have an idea of like what the target answer should be. So in a lot of cases, we can just do just exact matching, where we can parse the response from the model, locate like with some precision, like where the response is, and then compare that with the correct answer, and then just have kind of this, again, very binary idea of like, yes, it's an exact match, or no, it's not an exact match. So this is really difficult, as I said, for some things like, maybe like the reverse digit task. There's like not really any partial credit for like, maybe you start to reverse it and then you like lose the thread, or maybe you just like swap the order of two numbers or something. That's going to be treated the same as just like, not responding at all. So yeah, it's a lot easier to do the evaluation and things where it's like maybe a multiple choice or like, the flanker task where it's like you just pick a response and then we just look at that response and match. We can feel pretty confident that we're getting a good sense of what's going on. And yeah, those like longer tasks is a bit harder. Is that kind of what you were looking for?
Yeah, that's right. Thank you so much. Yeah.
Yeah, sure.
Just quickly, because we're past time. Psychologists often talk about a speed accuracy trade-off. That the faster you go, the less accurate you're going to be.
Right.
The slower you go, and it seemed like there's a little bit of an LLM version of that happening with the reasoning tasks, that they take longer but then are more accurate. So again, the it's not quite speed, but just length of process or efficient. This interested me because you talked about efficiency, and the length that they go through seems inefficient, but then arguably there's a kind of efficiency to getting the right answer.
Yes.
Whereas getting a wrong answer might be quick, but is not especially efficient because you ended up with a wrong answer. So just throwing out the speed efficiency trade-off as might be a useful point of comparison or something to when you're talking about the LLMs in relation to human cognition. And then the other thing was when the bookworm example is really compelling to me, and I even tested it for myself while you were talking
What did
on
you find? What did you find?
ChatGPT. 4 O's in bookworm. So
Ah, got
there
him.
you totally.
Who's the
And
5
but
PhD students in your pocket now?
um, what you said about LLMs not really being trained on the letters or to think about or to kind of that made a lot of sense to me. And thinking about some of the challenges with the flanker task kind of makes sense to me. And again, you're having to look at letters individually rather than whole morphs. But with the difficulty that the consistent and inconsistent stories are posing seems to be a very different kind of problem from the letter thing. Now maybe it's not, maybe they're the same, but to me that feels like just a different category of challenge for the LLM.
Yeah,
And I
I
don't have a good
agree.
description of it, but it just struck me as you were going through.
Yeah, I agree. My sense is that like the coherence with stories is a little bit more about like the construction of like a model of the story because
Mm-hmm.
like we're looking for like a violation of like that model of the story with the incoherence is at least my understanding.
Right.
Obviously still learning. But yes, I think the relationship is sort of like maybe if we start to look more, so one of the things that we want to look into for context for everybody here is that we want to start looking more into like what happens as we change like the length of the story and like the
Right.
distance between like whatever is incoherent and like the source of that incoherence in the text, which is where I think more of this like in context memory like comes into play. um but yes, I think that something like the flanker task also like there's a huge component of just like understanding the concept of like where you would look to look up
Right.
the central letter, I think is like one of the key difficulties for that one. Yeah, which is not too similar except for in the sense of like this like lack of groundedness, which is a very high level theme. But yeah, yeah, I agree.
Thank you. It's really helpful.
I have a question
Yeah,
only if folks have time for it.
I have time.
Cool.
Sure, go for it.
Because like I'm starting to get into NLP and
Ooh, let's
starting
talk.
about transformer
Let's
models
talk.
because it's gonna end up being important for my interests.
Okay, cool.
And so when you mentioned that like now I'm like LLMs kind of think about words and conceptualize words in tokens,
Yes.
not at the letter form where like our cognition is very adaptable for like
Right. Yeah, you can change your level of abstraction really easily, right? Or representation, yeah.
Yeah. So first question about that is like how does that work with like numbers?
Oh, like the tokenization for numbers.
Yeah.
Yeah, different models have different tokenizers. So different models tokenize numbers differently. A lot of them, so in our examples, we separate the numbers with like commas when we're doing the digit spans, which works really well to separate them into different tokens. If you have like just a long string of numbers together,
It treats it as like one number and not several digits.
oh, it will treat it as like, so some models will be groups of like 3 digits, groups of like two, sometimes like mixes where like one token is like 3 digits, the next token is like 2 digits. Like it can be a total mess. And I think that's why like, that was one of like the initial things that people would talk about, like after ChatGPT came out, right? Is like, oh, it's a computer, like it should be able to do math, but it can't do math. And like, yeah, as you're saying, it makes a lot of sense if you start to think about like, what is its representation of a digit? Yeah, yeah.
Because like when you were talking about the backward digit span,
Hmm.
I started thinking about like how like I mean you brought this up later about you brought up the token part later, but like words for LLM's sake have a very either semantic or categorical value.
Hmm.
Whereas like numbers can be like count like amounts. I don't know why I made those like those are kind of the same thing, but also
Right.
depending on like how you're counting versus how
Yeah,
you're
yeah, yeah.
accumulating. nominal, ordinal, interval, and also
Yeah.
ratio computational. Like, so
Yeah.
many ways you can interact with numbers.
Yeah.
That I'm just like, maybe that's like the wrench that's thrown in and screwing with LLMs, but also I don't know enough.
I see, I see. Yeah, so your idea is kind of like that maybe because the semantics of the numbers are not as clear as the semantics of words, that the lookup process is like harder.
Yeah, like
Yeah,
it's
yeah, yeah.
hard to like pinpoint like what level of not abstraction, but like if you're how do I put this? I don't know if there's like a mental list of rules that
Mhm.
ChatGPT or some or LLMs
Mhm.
have for like how to conceptualize numbers in certain contexts.
Yeah, yeah, yeah. Well, I think so I think there's definitely I think there's like a lot of merit to your intuition because another thing that we know is happening with language models is their processing is it's like there is like some level of like constructive representation that's like being built. So if you ever look at anything about like a residual stream in the language model for like the interpretability stuff. So I think that, yeah, what you're saying about, if it's true that the numbers have like a more difficult like interpretation, that yeah, maybe that does influence the way information is getting passed through this residual stream, which is in turn affecting like this lookup or recall process. Like, yeah, it could, yeah, seems reasonable. Yeah.
Lower level question.
Yeah, yeah, yeah.
For the digit span tasks, do you expect to see the same results y'all got if you use like alphanumeric values instead of solely numerical?
Yeah, so I have done like alpha only, so letters.
Yeah.
I don't know if alphanumeric implies that there are also numbers. So I've done only letters. And I was kind of interested in doing this because I wanted to see if there was any like letter level chunking. So like if I include strings like FBI or like CEO or something like that, does this like make it like better or worse? And I've only done like pilot for this rather than like a full thing. But in short, I did not see a difference between like the letters and the numbers, which like might not completely like disprove your point because like letters are also not really
Yeah.
like very strong like semantic whatever.
Yeah.
I don't know, maybe some of the people in here will have correct me on this. I could definitely be wrong. So yeah, and then with the chunking respect, I think we also like don't really see any difference between like the chunked or like not chunked condition, but maybe you would maybe if the task was like a little bit, you might need to find like a sweet spot for like the number of like letters that you're looking at. It might have been either too easy or too hard in my examples, which might have prevented me from finding any effect. But yeah, yeah. As you can see, there's like it's like time is like the main limiting factor. Like there's so many cool things that are so fun to try, and yeah, it just takes quite a bit to run like enough of the run inference enough time that you can like say anything like super definitive. So yeah, but yeah, definitely keep the all the ideas are great.
Sweet.
Yeah.
Yeah, thank you so much for taking the time to present. This is awesome.
Yeah, yeah, thanks so much. Really good to hear everybody's perspective. And yeah, happy to share any resources for like related work discussed. Fun fact, actually, especially is that at the conference I was just at, there was a paper about plot hole detection as benchmarking and finding that like they create some like intentional plot holes and find that language models have a very hard time finding these plot holes, which is very relevant to our recent like coherence work. So yeah, I'm gonna email that around to some of the coherence collaborators later. But yeah, anybody else is interested, let me know. And yeah, hit me up with any experiment or collaboration ideas or whatever. Yeah, always down to do more.
Sounds great. Thank you
Cool.
so much.
All right.
Nice.
Thanks, everybody.
Yeah. Bye.